All right, second day of notes for Chapter 3, Lesson 3. We're on the section called Plate Motion. Coming over here and skipping a line, plate, capital P-L-A-T-E, motion, capital M-O-T-I-O-N. Plate motion. Pencil. How do tectonic plates move across Earth? Recall that Earth's interior is much hotter than its surface. This temperature difference causes a convection current to form in the asthenosphere. So the interior is hotter. That hotter material becomes less dense and rises. As it gets near the outer surface, it cools. Some of it turns into crust, while others of it create these convection currents. And that spinning also causes the crust to move in the same directions as the swirling mantle. Okay, convection is the transfer of thermal energy by the mass movement in a fluid, such as air, water, or molten rock. In a convection current, convection drives the fluid through a circular path. Okay, so do we know that the interior is hotter than the exterior? I think we do know that. Let's go ahead and use this picture up here. We're going to say interior, I-N-T-E-R-I-O-R. Up here, we're going to say exterior, E-X-T-E-R-I-O-R. And let's just go ahead and draw a line like that. And somehow we'll go around the cool on top of it like that. And that is the crust, C-R-U-S-T, C-R-U-S-T. Okay. Notice in theirs they show the crust, they also show the mid-ocean ridge. All right, so let's continue our crust right there in a little uprise. Let's draw an arrow because the magma comes up out that way, and that is the mid, M-I-D, dash ocean, O-C-E-A-N, ridge, R-I-D-G-E. That's where the mid-ocean ridge is. Oh, you know what? I did not draw this correctly. Okay, so we're going to fix our picture. We're going to have this arrow come up this way and draw another one right there next to it. We're going to erase these two arrows and this arrow. Okay, so we have that swirl kind of going to the left, just like here. Now we're going to make a swirl going to the right. Okay, so we're going to draw an up arrow to the right, coming around and down this way, back over, and then up that way. So now we very clearly have one swirl to the left, one swirl to the right. For the heat magma, we're going to change the double arrow to be right in between those two, and we're going to get rid of this one. Okay, so now, in the interior, in the mantle, M-A-N-T-L-E, we have the heat, or the magma, pushing and lifting things up towards the crust. When those two plates split open, that's where the mid-ocean ridge is. The crust either goes off to the left, and we can draw a little arrow on the end of the crust because it goes that way, or a little arrow on the end of this crust because it goes that way. And then as the mantle and magma lifts and rises, some of it cools down and stays in here, creates that convection current there to the left, or a convection current to the right. And it drives it in a circular path. Okay, now we fixed our drawing, and that's good. Convection currents form in Earth's atmosphere in oceans, in an aquarium, and even in a pot of water heated on a stove. Okay, so these convection currents happen with any fluids. In a heated pot, the water near the bottom heats up first. The hot water is less dense than the cooler water above it and rises. Okay, so we talked about that density, right? The granitic rock that's in the continental crust is less dense, and that kind of helps it float. The oceanic crust is basaltic. It's a little more dense, so it sinks. Cooler, denser water moves in to take its place. When the hot water reaches the top of the pot, it cools, becomes denser, and sinks back down to the heated again. So, hot down here at the bottom, it lifts up, it gets cooler, some of it will turn into crust, others of it will kind of move and swirl, and as it cools it gets more dense, drops back down. When it gets to the bottom it starts heating up again, starts getting less dense, starts wanting to float, and moves up again, and that's how you get that circular convection current. Okay, let's see, where are we? A similar process takes place in Earth's interior. As rock material is heated deep in the asthenosphere, that's deep over here, it expands and becomes less dense. Because it is less dense than surrounding rock, it rises. Eventually it cools, becomes denser, and sinks again, forming a convection current. So it cools, becomes less dense, sinks again, and starts that current motion. Gets into the asthenosphere, heats up, less dense, floats and rises, cools, more dense, sinks towards the bottom, and so on. The asthenosphere contains many slow-moving convection currents. According to one theory, these currents move the tectonic plates above them. They drag plates along, much like a conveyor belt drags groceries at the supermarket. Okay, so if all this Play-Doh-y material down here is swirling, then it's kind of dragging the crust along with it as it goes. So, next here to plate motion, we can say that the currents, C-U-R-R-E-N-T-S, quote-unquote, drag, D-R-A-G, the crust, C-R-U-S-T. All right, according to one theory, convection currents in Earth's mantle drag along tectonic plates. Here, the currents move two plates apart. So that current, when it gets up here to the top, kind of drags the crust to the left. And then this current, as it gets up here to the top, it drags that crust to the right. And that's why they split open at the mid-ocean ridge. So, currents drag crust / plates, P-L-A-T-E-S, because remember the plates are the crust and the upper mantle. All of that together is called the lithosphere. All right, let's see. Slow motion. Do we have enough space to start slow motion? I'm going to say yes, because we can always go to the back side. So, red pen, red pencil, skip a line, slow, capital S-L-O-W, motion, capital M-O-T-I-O-N. Pencil. As you might guess, tectonic plates move very slowly. Recall that Pangaea started to break up about 200 million years ago. It took millions of years for the supercontinent to break apart, and millions more for the modern continents to move to their present positions. So things are moving so slowly it takes millions of years to move to what we have today. Okay, slow motion. Millions, M-I-L-L-I-O-N-S, of O-F, years, Y-E-A-R-S. Scientists have measured tectonic plates moving at an average speed of about 10 centimeters per year, or 4 inches per year. Okay, so we're going to do squiggle next to millions of years. 4 I-N period / Y-R. 4 inches per year, about. All right, so basically what they're saying is, here's California the way it looks today. 1 year from now, things will move about 4 inches. Not very much for us. That's about 4 thumb widths. Probably about that far, probably about as wide as your hand. That's how fast things move in 1 year. Okay, where are we? That is about the rate at which fingernails grow. Oh, okay. So 4 inches per year, that's about how fast a fingernail grows. F-I-N-G-E-R Nails, fingernails. However, this slow rate of movement adds up over time. Suppose that a plate moves at a speed of 2 centimeters per year. Okay, notice that's a lot slower. That's only 1/5 or 20% of what they were saying up here. Over the course of 100,000 years, the plate will have moved 2 kilometers. 2 kilometers, that's probably somewhere around a mile. Over 200 million years, the plate would have traveled some 4,000 kilometers. Okay, so even though it's moving very slowly about the same rate as your fingernails, if you go over the course of 100,000 or even a million years, things move pretty far. What kinds of changes can slow-moving plates cause? The answer includes mountain building, earthquakes, and volcanoes. Okay, so let's see. Mountains, M-O-U-N-T-A-I-N-S, zoop. Earthquakes, E-A-R-T-H-Q-U-A-K-E-S, zoop. Volcanoes, V-O-L-C-A-N-O-E-S. You will learn more about these changes in the next chapter. You might think that Earth would be a better home without its tectonic activity. However, Earth scientists would argue otherwise. Without mountain building, for example, the forces of weathering and erosion would gradually flatten all of Earth's landforms. How do you think flat continents would affect life on Earth? Okay, well, if things were perfectly flat, I would think that it would be easier for floods to happen. I would think that actually there would be a lot more water over the surface, so we wouldn't have as much surface to live on. A lot of things would change. Okay, so all these mountains, earthquakes, and volcanoes, let's draw a little arrow to the left, enable, E-N-A-B-L-E, weathering, W-E-A-T-H-E-R-I-N-G. Notice how they are connecting everything we have learned up until this point to each other. So they're connecting the structure of the Earth, they're connecting tectonic plates, they're connecting the movement and the convection currents, and they're even connecting weathering, erosion, rivers, everything we were learning about recently to each other. All right, let's look at the picture. Tectonic plates of California. Here's California, Sacramento, San Francisco, Fresno, Bakersfield's probably right around down here somewhere, which is pretty close to Wasco. Okay, that line is the San Andreas Fault. Notice the arrows are moving past each other. So this purple plate is the North American plate. It's moving that way. The orange plate is the Pacific plate. Includes all of that continental crust and all this oceanic crust. And that's all moving that way. So they are moving and sliding past each other. Notice how all that pushing against each other causes these mountains here and causes all the hills and mountains all along that edge, all up and down the coast of California. Okay, what's our question? What would happen to tectonic plates if Earth's interior cooled? Okay, well, because the interior is hot, that causes the magma to lift or rise to the surface. That drives this circular path of convection currents. That creates the mid-ocean ridges where the crust splits apart from each other. That also allows the continental crust to slam into each other and cause mountains, earthquakes, and volcanoes. So if the Earth's interior cooled, this whole process would stop. There wouldn't be any convection currents. There probably would be no difference between the continental and the oceanic crusts. The plates would not kind of like float on top. It would all just become solid rock. So there wouldn't be any plate motion anymore. So then you would not get mountains, earthquakes, or volcanoes. So then the Earth would just be flat eventually. Okay, so you see how they ask a question that's the opposite. All of our notes talk about the interior being hot. Their question is the opposite. Make a prediction, right? They're doing a phase 3 connection question here. Predict what would happen if everything in our notes was the opposite. All right, good job persevering on day 2. Good job having a growth mindset. Roar Wildcats.